here on this side of the coast. We've been fairly lucky in terms of COVID. We've about into our second week of totally free. So most of our restrictions have been lifted, but wherever you are in the world, hopefully you're following your local guidelines. We want to have a happy and healthy community when hopefully one day we can meet each other face to face again. This is how you get in touch with me. I like talking tech, although this one is a fairly high level talk. Not a lot of tech in this one, more like a historical tour. But yeah, please reach out to me on Twitter. I have a blog, and if video's more your thing, please jump onto my YouTube channel. I could do the cool kids say and say smash that like button and subscribe to that stuff. But yeah, if you enjoy tech content via video, jump onto my channel. But yeah, please follow me on Twitter so we can stay in touch in these times where we can't physically meet up. I will say, I need to give a big thank you to whoever's on this call, because I worked out, this is my 29th webinar this year, and this is the first one I've given in normal business hours. It's 2 p.m. here for me. Every other webinar so far this year has been before 8 in the morning or after 6 p.m. at night. So I'm actually thrilled that I actually can do a talk during the day. Very, very nice. We're going to talk about the rise and fall and the rise again of SQL databases. Really a historical tour through data itself, and hopefully to bring us up to where we are today and finish off with hopefully some advice for you as to where I see things are going. So as I said, it's more of a journey down memory lane as opposed to a great deal of tech in this one today. Now, I'll start with a picture of my two children. This is Max and this is Aiden. They're in their early teens. And because they're young men growing up, obviously they need mentors. They need things that they can rely upon as the most important thing in their life. And yeah, you would imagine that should be their father. That should be me. But of course, that's not the case. The most important thing in their life, like every teenager, is their phone. That's the thing that drives them at the moment. That's the thing that guides them along their path, sadly. And inside a phone nowadays, it's insane what you can fit in a phone. You can buy terabyte SD cards. That's something like the size of my fingernail that holds a terabyte. And as a result, we take data for granted, or just the volumes we can store. But if we go back in time, data was actually a lot smaller. And in fact, not only smaller, data just didn't exist from a computing perspective. There literally was no data. Now, what do I mean by that? Let's go back and look at the very earliest computing devices we had that we would still call a computer. This is from the 40s. This is literally called the ABC. It's the Antennasoft Berry computer, one of the very, very first production computing machines we ever had. And it didn't actually have memory even. The way you fed it, information was actually on a paper tape. And this isn't like the equivalent of its disk drive. This is the equivalent of its actual memory. Memory access in the very first computers was sequential. The concept of RAM, random access memory, just didn't exist. As a result, the arrival of data was a big thing. Once we got to this level of machine, this is the ERA 1101, this was a real landmark jump in computing, where we could actually have data that was stored on some sort of medium and could be read and presented to the machine. And how do we present it to the machine? We presented it via tape, generally. And so the ERA had a little bit of memory as opposed to the ABC computer, or the ABC, but most of the information came in still in a sequential mechanism coming from a medium such as tape. So yes, we had data access now, but data access like the ABC computer was now sequential. If we move on to the 1950s, we had this landmark invention, that of disk. And disk it wasn't the fact that we had a new medium, it was the fact that we had the ability to do random data access as opposed to sequential. This was the real sort of changing moment when it came to the concept of data and databases. Here's a picture of one of the very first random access disk drives. This was made by IBM, and yes, it held a whopping great 5 megabytes of data. Now, so we'd gone from no data to small amounts of data. Now, when I say small, 5 megabytes is obviously tiny to what we think of today. But when I say small, I mean it's small in terms of capacity. Because that picture I just showed you of a 5 megabyte drive, To give you some sort of perspective of the scale, if you wanted to store your favorite Tones and I Dance Monkey soundtrack, which is about a 5 megabyte MP3, you had to ship that 5 megabyte drive onto an aircraft to get it to you, because literally it was the size of a couple of refrigerators. That's the size of the original 5 megabyte disk drive. But we had random data access. That was a real transformational moment in data processing via a computer. That led to data access algorithms. If you can access data not just sequentially, now you need to come up with mechanisms to best access data. And that came to data access algorithms, which of course leads to what we call databases. And that's the very first inkling of the concept of storing information on a database. Now, a database really is nothing more than random access to storage or data, but in an intelligent fashion. We're trying to wrap the very core principles of data access with some sort of intelligence in order to access the data intelligently. In the 1960s, you could argue our first attempt at this was a thing called ISAM, Index Sequential Access Method. And as the name suggests, we have some sort of indexing mechanism which allows access to the data. But it really was, when you had these systems called ISAM, it was the only access method. The mindset of today of how we can access data in different ways didn't exist back in the 60s. ISAM literally was, you have an index, and that is the only mechanism by which you can access data via an index scan. To help explain how these things worked, let's look at a bit of a shopping metaphor here. I might have a file. We didn't have tables in those days because relational databases didn't exist. I might have a file called shop, and I should have a ISAM database called shop, which would consist of one or more files. Each record in those files would typically be of a fixed size. And so, for example, here I've got some various shopping centers from around Europe. The way we would access them is we would store another flat file, literally called an index, where the index keys would be stored in alphabetical order. So Harrods comes first, Palladium comes last, etc. And it would contain an offset to where that record in the file was. It's not too dissimilar from the way we use indexes nowadays, except we don't use things like B trees. Back in the days of ISAM, the only way you could access data would be simply to start at the top of the index and work your way down. Now, obviously, what happens when we want to change data or add data? If I added a new shopping center, the way it would work back in the 60s is that would be added to the end of the index file. And then obviously now the index file is no longer in order. It's not like a B tree. And what would happen is once a night, etc., you would scan and rebuild that index and resort it and put it in order. But index reads would scan top to bottom through the index and find the right information in your flat files. Hence the term ISAM. An only mechanism is an index sequential scan of accessing your data. If you had another in ISAM database called products, which map to shops, you might have jeans, handbags, etc. How do we know where these things are related to shops? Well, it was actually the job of the developer to do that. So the developer had to code up all the access through those files. So if I want to see, for example, I want to buy something from a shop, I would open the shop index, I would scan through it until I found the shop I was interested in. And once I found that, that's where the shop was. And I would simply store that. And then I would open up the products flat file and I would scan through the products index, read through that. And if I want to buy milk, for example, I'd find milk and then I'd read that. So the developer literally had to work his way through these files via their index bit by bit. And all the relationships between these particular files was the developer's responsibility. I would read the shops, I would read the products, and then I would actually look in the products file. For example, does byte 30 to 40 contain the name of the shop I'm interested in? And so that's literally how you would do a join in those days. You would actually read separate things, and in your code yourself, you would effectively architect the join concept. And that's what ISAM was. ISAM was obviously fairly limited what it was do, but don't forget, this is the days of very slow computers, very slow mainframes, etc. Someone's popped something in the chat. That's just the tour saying, yep, use the Q&A if you have questions. The logical advancement of ISAM was the first what we call hierarchical databases. Hierarchical databases started to build the relationships between data artifacts into the technology itself, as opposed to being entirely the responsibility of the developer. So now I could have a hierarchy of data. For example, for my first shop, I could sell, well, it sells jeans, phones, and milk. My second shop, Palladium, it sells jeans and phones, etc. There's now an understanding between different artifacts about how they're related. And similarly, because it was a hierarchical database, they were the first databases to actually allow multiple levels in the hierarchy. For example, a phone could then consist of a Galaxy S10, an iPhone 11, etc. We have now nesting of levels inside the hierarchy. Even so, with these hierarchical databases, the developer still had to define all the access to get through them. So the kind of code you would write would be, for example, starting at the highest level of the hierarchy, get this particular shop with a unique key. And then once I've got that, I would then what's called get next child, which simply says what's the next level in the hierarchy. It's a list of products. I would loop through them until I find the entry of phones. That gives me a key to the next level of the hierarchy, which lets me loop through that, getting the next child until I find an iPhone 11. And that's how I buy an iPhone 11 from the phones product from that particular shop. We do these hierarchical descents using code. But it was still a jump forward from ISAM because rather than the developer having to code the access and infer the relationships, now the relationships were implicit. Now, for small data, that was generally okay. But in the 1970s, things started to change, in particular in terms of hardware. We started seeing the first mini computers and mainframes, and we started seeing the technological advancement of hard drives. This was one of the first 200 megabyte hard drives, which was absolutely massive in the 70s. That was an enormous piece of kit, a 200 megabyte hard drive. As data exploded into these huge volumes, hierarchical databases were starting to show signs of wear and tear. And this was obviously the landmark moment where probably the founder of relational database theory, Edgar Todd or Ted Codd, came up with his landmark paper, this being one of the key paragraphs. Data is represented as mathematical n-area relations, and n-area relation being a subset of the Cartesian product of n domains. Now, being a relational database person, I don't know about you, but when I see that, I'm totally mystified as to what it means. I have no idea. It's very much based in algebra, not really in terms of what we would think of a relational database. But the advent of relational database theory was fairly simple in the sense that where we used to have flat files and records, that we could model the information that we currently have on our disk drives actually with mathematical algebraic theory or set theory. So it looks very similar on the screen there, but really this was more of a jump in terms of how you understood data. Rather than being rows and columns, it was a set of tuples. And that was Ted Codd's major sort of breakthrough. We could actually use set concepts to map to understand data, and set logic was a well understood mathematical discipline, so we should be able to take advantage of that. Ted Codd worked for IBM. He came up with this seminal paper. He presented it to IBM and said, I've got this amazing idea for how we could actually remap how we understand data. And they pretty much said, no, thanks, we're not interested. Why would they say that? Well, the biggest vendor and the most successful vendor of hierarchical databases in the 70s was IBM. They were making a bucket load of money off their hierarchical database technology. Why would you abandon that and adopt a new one? In 1979, someone came along and took advantage of IBM's hesitance in terms of jumping on that bandwagon, and that was a company called Oracle. They were one of the very first people to build a relational database based on Ted Codd's set of principles. One of their first customers was the CIA. They were happy to take a bit of a risk because they were looking for transformational technologies in which data could be obviously securely and stored and obviously accurately queried. So relational theory led to the first relational databases. And this is probably the mid 80s, they just took over the world. If you look at the timeline of of releases of vendor different databases, throughout the 80s and 90s, all of the big players, most of which are still around today, was when they had their founding moment. And so throughout the 80s and 90s, relational databases literally became the dominant paradigm in data storage technology. Now, the big question is why? What did they offer us over the very successful hierarchical databases that have been running on mainframes in particular since then? One of the reasons was data capacity, while it was growing, was still insanely expensive. Nowadays you can go down the corner store and get a terabyte for nothing, but in those days, disk drive technology was still very, very expensive. And the concept of relational modeling rather than data duplication and the various normal forms that we had through Ted Codd's work led to things like the ability to compact the amount of data to its best degree. So, for example, if I have a list of employees and you can see the third attribute there in each tuple is the department, I could create a departments set and then map the two together using just their surrogate keys. Third normal form, and for those who are really into it, the fourth, fifth, and sixth normal forms led to a mechanism of making sure the data could be as compact as possible, therefore getting the most out of the expensive data capacity. Also, the big thing really was the concept of data accuracy. Relational databases were one of the first things to introduce the concept of transactions. Hierarchical databases generally didn't have the idea of commit and rollback. It was very much like you just did work and it was done. If you needed to roll it back, you had to write work to undo it. And transactions obviously are very, very important in modern day societies. If I withdraw $157 from my account such that I can pay my electricity bill, and then I deposit it into the electricity company's account, well, it's pretty important to me that either both of those things work or both of those things fail. I don't really mind which way or the other, as long as it's one of those two things. The worst possible scenario would be for me to lose my money, but the electricity company to say they never got it. The importance of transactions was a real sort of jump for development of applications because it took away a lot of the worries of data integrity from developers. So most of us are now familiar with the concept of ACID. That was one of the big banner headlines of relational databases. The third one was storage independence. And we take this for granted nowadays, but if we go back to before relational, if someone gave you this as a developer, go find Maria's details and derive a 10% commission. An ISAM or a hierarchical database program might look something like this. You had to know the list of the files where Maria's data would be, or all the employees' data might be. And then you needed to move Maria to the particular key item. But then when you read it, you needed to know what particular bytes of the resultant records contain the information you needed. And then you could do a computation. With relational set theory, you didn't need to know that. Here is the set-based expression. I want to create a new set where I take the existing details for the database called Oracle, where the name is Maria, and times the salary by 0.1 to derive a commission. Now, in there's no references to files, there's no references to computer program, indexes, etc. It's really a expression of what you want to achieve, as opposed to what are the actual physical details of actually achieving this. This was a big deal. This was the first time ever you could ask for data from a database system or from a computer without actually knowing how it's actually stored. This was huge because it was the first time ever people didn't have to be low-level system programmers in order to access data. That led to one of the first what we call SQL-like languages called Quell, and it looked a bit like this. It's similar to modern SQL, but you can see where the origins of SQL have come from. We would say the range of this set called S is the employee, retrieve that into a new set called S1, and as I build that set, I'm adding elements called employee ID, name, and department, and the commission is a new element based on the existing salary of 10%. And then I'd have the where clause at the end. So it's closer to set theory than what we would think of SQL, but that was probably the first ever query language that was based on relational databases. That led to SQL, which led to what we call modern SQL nowadays, which looks a bit like this. And you can see there's certainly some comparisons there, some linkages back to the original query languages. Similarly, when we got into our set theory, as we saw before, where we had multiple sets and we wanted to join them together, SQL obviously allowed for that as well. And I'm sure everyone on the call is very familiar with how to do joins. I've put the ANSI join here just to show how modern and cool I am as a developer, even though my preference is probably the old Oracle style syntax. This was not, sorry, let me start again. Not only was asking for data without knowing how it's stored critical, it was the first time ever we didn't have to know how to do it best either. We could actually offset that to some other piece of technology. We know it nowadays as the optimizer. For example, if I gave you a query like this, go get all the departments and employees where the employees are less than 20 years old and the location is Baku, which is Azerbaijan's biggest city, I should probably start with the employee tables because there's probably less employees under the age of 20. That's the smaller set, and then join into departments. But if the query was like this, employees under the age of 80, which is probably all the employees, for Bada, which is a very small city in Azerbaijan, then I would probably start with the departments table. Relational databases were the very first pieces of technology where the database itself could decide how to best get the data, as opposed to you having to programmatically know in advance. What this meant was, if you consider during this time also from a hardware perspective, we were going from mainframes, only available to businesses, etc., to PCs. It was called the consumerization of IT hardware. Mainframes, reserved for the elite, i.e. companies. PCs, anyone can have one and they can do things with a computer. Relational databases from hierarchical were actually the consumerization of data. If I wanted to manipulate data or read data, I didn't need a programming degree. I didn't need to know how to write COBOL or some other language. I just had to use a friendly language like SQL, and something else would take care of getting that data in the best way. So we moved from a situation where the program, your ability to write code was valuable, to now the data itself being valuable. That was probably the biggest thing that relational databases brought to the table. Now, relational dominates today still, and it pretty much dominated until this particular moment. Now, what moment's that? That's Y2K. Now, we're not talking about the Y2K bug here. We're talking about after the year 2000, two big things happened. Number one was everyone started consuming data. And why did they start consuming data? Because of this thing called the internet. This was a graph of the number of websites per year. And you can see past 2000, when the internet just started exploding, everyone started either having a website, reading a website, etc., hacking a website. But yeah, the absorption of internet or the absorption of data via the internet just went through the roof. The second thing is everyone started producing data. Why? Because we started off with smartphones and also more access to the internet with modern computing devices. These are a couple of pictures that my friend Guy Harrison shared with me a while ago. This is a picture, if you look back, I can't remember what year it was, might have been 2004, I can't remember, when Pope John Paul II was being his swearing in effectively. If you look amongst the crowd there, you can see there's maybe one person with some sort of smart device. Fast forward a few years to the next Pope, and there's the same place, same ceremony, and times have changed just a little bit. It's what we call the Industrial Revolution of data. If you go back to the Industrial Revolution in its classical sense, we used to manufacture things by hand. If you wanted to make, anything like out of silk, you would actually have a human do it for you. And then we invented machines to do it for us. The same thing happened with the Industrial Revolution of data. Rather than data being produced by humans, someone keying it in, data was now being produced by machines. And in fact, Eric Schmidt, the CEO of Google, said, as much data is being created every 2 days now than is the same as from the beginning of time to the year 2003. And he said this in 2010. You can imagine what it is today. The amount of data production is just off the charts. To show you how ridiculous it's getting, you can now buy a water bottle that will Bluetooth connect to your phone and tell you when it's getting empty. Here's a water bottle. It's pretty easy to tell when that's getting empty. I just I look at it, or I shake it even if it's not clear. But who knows? Now we have Bluetooth enabled water bottles. It's out of control. So before the year 2000, the value of data was in its quality. You made sure it's accurate, you made sure it was well defined, it was rigorous. That's what relational databases really offered us. After 2000, the data value really became about volume. How much can you consume, because somewhere in there could be some value. And hence the evolution of what we call big data. And you look at the companies that really prospered in the early 2000s in terms of taking advantage of the internet, and it was these people that were prepared to embark upon the value of vast volumes of data. That was a bit of a real change up, a real sort of, not a threat, a change of perspective to the dominant database players at the time. Because the dominant database players, Oracle, IBM, SQL Server, etc., all the relational databases, were vastly capable for dealing with thousands of users and terabytes of data, which in those days was insanely big. But all of a sudden, we needed database technologies that could deal with millions of users and petabytes of data, and they probably weren't up to the task at that point in time. In those days, the way you scaled data was, as your user community grew, you got a bigger database and a bigger server. But obviously there were limits to what you could do. Thus, the Googles and Facebooks and Yahoos of the world couldn't do that. There wasn't simply a big enough server. So for them, they said, we'll just add more servers. So rather than having a one server that got bigger, they just added more and more and more servers. The problem with that is how do you then present a single database that sits on top of that? This is one of the first Google data center, from its early origins. Nowadays, and even this photo is now a decade out of date. Nowadays, it's literally millions upon millions of servers, and yet you still want to present the view of a logical single database. To do that, they had to invent their own technology because the technology didn't exist. So we had Google File System and Google applications run on top of the Google File System. Out of that came an open source equivalent known as Hadoop, which really is the same metaphor. You have a vast number of servers. You have the Hadoop file system, HDFS, which is implemented in Java, sitting on top of that. And then you could build your own applications as opposed to running Google applications. But this was the first real jump into the concept of, if I can't run a database on a single server, I can run an equivalent thing on multiple servers. Yahoo, probably less popular nowadays, but back in the day, they had one of the biggest Hadoop clusters ever. Even back in 2012, they had a 42,000 server cluster farm. That's how massively of scale these multiple server databases became. That gives you unlimited size, it gives you unlimited scale, it gives you unlimited everything, but you have to have a sacrifice. If you have more than one server and you want to present a logical single database, you have to partition the data across those multiple servers. It's called sharding. When it comes to relational modeling, it probably doesn't sit so well in the concept of sharding, because a relational model has this assumption that underneath a table called, for example, department, is a logically correct set of data called employees for that department. Well, in a multiple server world, the department table might be served from one server and the employees might be served from another server. And what if they can't talk to each other for some reason? Then we end up with all sorts of data inconsistencies. To solve that, a lot of people moved away from aggregate modeling into what we call single table modeling. Rather than separate department and employee, which therefore might sit across different servers, what we'll do is we'll jam them all in together. We'll have a single table called department, but it consists of all the employees as well. It's basically a single structure. Because of that, I only have a key to the department, and when I use that, I can get all the employees and the department details as well. All the value sits under a single key. The reason that's useful in a multi-server environment is, rather than splitting the data in terms of different tables across different servers, I split the data based on keys across different servers. So if I'm looking for the department called sales or employees for sales department, I put it through a hash function that tells me what server the sales department will be on, and that's where it's going to be. That's how we do data sharding in a database that sits across multiple servers. That led to what we call the NoSQL model. If I don't need joins, if I don't need multiple tables, I just have a single table, then I don't need the SQL interface. So NoSQL is actually a terrible, real name. It really meant non-relational. We're not doing relational modeling, we're doing single table modeling. Plenty of NoSQL variants have come around during this time frame. The first and most simple were key value pairs, and there's some examples of some of those ones that have evolved over time. And key value pairs, as the name suggests, you have a known key, a meaningful key, like for example, an engine ID for a vehicle, and then the data is generally what we call opaque. It's in some sort of internal format that only makes sense once it's presented back to your application. Thus, you can only do key lookups, but that's still pretty useful. The application is responsible for all the stuff after that. You can do key lookups, but everything else is the application's job. As a startup, that's great. If you're doing session state, prototyping, shopping cart kind of stuff, where the only access you'll ever do is with a key value pairs are fine. We then evolved NoSQL to be a little bit more sophisticated, to be document style. It's still generally key lookups. These are some of the examples of them. But now the actual value element, rather than being cryptic or internal, is now observable. The most common examples are JSON and XML structures. For things like event logging, content management, IoT device, anyone writing in JavaScript, where you can directly model JSON into an object, these kind of things were very, very useful. So it's still key value lookup in general, but the value is actually observable and therefore searchable. They evolved even further to what we call column store style databases. And these are some of the examples: Cassandra, Bigtable, HBase, which you can almost think of conceptually as key value pairs of key value pairs. So you might end up with something like this if I'm modeling, say, people. The first person, citizen number 1, I might have their email, their name, their surname. The second citizen, another key value pair, might just have their account number and their bank details. So this is very good for applications that evolve over time, because each key can actually consist of different attributes. For ad hoc search, data evolution, they're very, very good for this. Facebook uses this, as you can imagine. So if we have a quick look at where we're up to, we went from ISAM back in the 60s to hierarchical databases, to relational databases, back to ISAM, which is basically key value lookup, and then we went back to hierarchical, which is effectively aggregate table modeling, where we have key value pairs of key value pairs. We've sort of come full circle in a sense. And just like the 1950s, there was no schema. Hence, you'll probably hear the term schemaless in terms of schemaless applications. It's not really schemaless. What we've really done is the application is now responsible for the schema, not the database. The schema has moved to the application. Developers love this because you no longer have to deal with whoever's looking after the relational database authority, like the DBAs. There's unlimited flexibility. I don't have to worry about data modeling. I can just start throwing documents into the database and change them on the fly. I get unlimited volume and generally unlimited performance because I just keep adding servers as we go. So NoSQL seemed to be the future until this thing came along to throw a spanner in the works. The CAP theorem. Eric Brewer came along in 2000 and said, the CAP theorem is, there are 3 things you would like to have in any effectively distributed system: consistency, availability, partition tolerance. And what are they? He said it's impossible to have all 3. The 3 are consistency. Whatever node you visit, you can get the same view of the world. Availability means if you blow away 3 nodes, the other nodes still work fine. Partition tolerance means if the nodes can't talk to each other, then we can still achieve all we want to. The system still stays up and running. And he said you get to pick any 2 of them. You can't have all 3. I thought I'd show you this with an example using a very simple Venn diagram. Partitioned and consistent. If I have a petrol station, and I have lots of petrol stations, which means it's partitioned. If one of the petrol stations has this price, but I lose one of the other petrol stations, I can't access it, their phone line is down. Partitioned and consistent means I have to take all the petrol stations offline, otherwise one of them might change their diesel price and we might not know. So I can be partitioned and consistent, but I can't be available. If I want to be available and consistent, that means I have to have one petrol station. Because if I was to have more than one petrol station, then I can no longer have partitioning. And if I want to be partitioned and available, it means I can have one petrol station that shows this for its diesel price. I can show another petrol station that might show something different. Because if I can't talk to them and I don't want to take the system down, then obviously I can't control what price they've got. So I'm not consistent. I'm partitioned, available, but I'm not consistent. What we're hoping for is over time that they'll be able to talk to each other and therefore become consistent. If anyone tells you that they're all three, that's really what we call a magical land where fairies and pixies live, because it's very unlikely. So in the big data world, you have to have P because you have multiple servers, which means you must choose A or C. It can be pretty successful. It can be pretty unsuccessful. Now, what I mean by successful, a lot of companies have really bet their farm on NoSQL and have done very, very well. Some people have started with NoSQL solutions where they've gone with these eventually consistent systems, and they've had to back away from it. This is a quote from Facebook. They started with an eventually consistent system and then moved away from that because it was just very hard to manage. So if you've got really good developers, you can succeed at this, but it can be quite difficult. But I don't want to be, raining on NoSQL's parade. It's been very, very successful. There's plenty of vendors out there that are doing very, very well with predominantly NoSQL style solutions. I got to keep an eye on my time here. Big data, not so much. Big data became this real buzzword for a long, long time, but there's not a lot of buzz about Hadoop anymore. And the reasons really for that were, one is it was generally fairly slow. Data science is actually harder than we thought. A lot of us thought if we just collected as much data as we possibly could, then somehow we'd find some incredible value out of it. But ultimately, we actually found that it's actually not. We in general got a lot of data, but we didn't get a lot of value out of that data. Here's an example of the kind of things that you could do with big data. Here are two sets of data. It looks very strong between them that, there must be some relationship here. Turns out it's the amount of cheese people ate versus the amount of people who die getting strangled by their bed sheets. Then we can pretty safely say there's not a lot of correlation between them. But if you collect enough data, you can almost come up with any conclusion. And the other problem was, to access big data systems generally required Java. And in 30 years of data access, SQL was the language of data access. That's what people had become familiar with. To tell them, no, you have to do it with Java nowadays, generally didn't go down well. SQL was particularly easy to learn, whereas Java for the non-IT person certainly wasn't. So SQL you can think of as the de facto citizen language. And it's funny how the people that invented NoSQL systems, Google, Facebook, started realizing that, guess what? NoSQL meant, we're going to need some SQL. And it's funny how all the NoSQL implementations nowadays generally led to SQL platforms on top of it. We got Hive that sits on top of Hadoop. We got Tez, we got Impala, we've got Kadoo, we've got Presto. I think there's Parquet, we've got Apache Drill, Spark SQL. A plethora of platforms on top of big data systems, all about putting a SQL language on top of NoSQL systems. Okay, we're nearly here. We're nearly up to date. Once we get to the 2010s, what's the big metaphor? It's about cloud. And cloud is important because if you look through this history, people who have adopted it, companies out there, they said, yep, we need relational databases. I got some Oracle, I got some SQL Server. Oh, NoSQL seems to be popular. Okay, I need a Hadoop cluster. Oh, I need some big data stuff. I'm going to use Spark. Companies had a plethora of different technologies as the world evolved. All that stuff is hard to manage. They went, you know what, the best way we can handle this is put it on cloud. You know why? Because it leads to this important acronym, SEP. SEP is, it's someone else's problem. And that's one of the joys of cloud. You make it someone else's problem to deal with all that complexity. Once you start talking about databases on the cloud, we start talking about distributed databases. And the next big thing seems to be what we call distributed SQL databases. You look at these kind of vendors that have been coming up now, and they're talking about relational database technology on the cloud. This is a quote from the guy that was one of the founders at YouTube in terms of their tech department. And he always said, if we'd had relational distributed databases, we would have used them. The only reason NoSQL database even started was we couldn't get relational to scale. So if you can get a relational database to scale to your needs, that's probably the best option. When it comes to cap in the cloud, though, surely I'm still going to have this problem, the cap theorem. Well, nowadays networks are incredibly resilient. Google, Oracle, all the big vendors are putting incredible redundancy into their network, which means if you never lose the network, you never have to worry about partition tolerance errors. So maybe you can actually have your cake and eat it as well. And then we have these things called cloud native databases. That's pretty much where we're going. The fact that we can have a relational database sitting in the cloud and still not have to worry about the cap theorem. So what about the future? Where do I think the future? What's important in the future? Well, I think there's been a big shift in terms of security, and that is people nowadays will forgive you if your site goes down. You look at some of the big outages we've had lately. Delta were down, Office 365, Azure, and Google had a cloud. Amazon had a massive outage in Sydney when they had a big storm there. No one said I'm never flying Delta again. No one said I'm never using Amazon or Google again. But what customers don't do is they won't forgive you for being hacked. That's for sure. If you get hacked nowadays, you are out of business. And let's face it, we've had some major big examples of major corporations getting hacked. This one actually got put out of business simply because security has become that much more important. So one of the things I think will become much more incredibly important nowadays is security technologies in databases, things like blockchain and the like. So what's my advice for the database professional? What do I see the future in terms of what I think you should learn? The amount of data will tend to infinity. I don't think that's ever going to change. I think the amount of data we're going to collect is just going to keep growing and growing. Let's face it, you can put a terabyte now on something the size of your fingernails. To give you some perspective, if we look back to our 5 megabyte drive, to get a terabyte of them, I would need this many of them. Now, when I say this many of them, I need that and then 1,000 more pages of that. That's how insane the data volumes are nowadays. So if you're a fresh developer coming out of graduates, I know the temptation is I want to be a game developer. I want to write the next Fortnite. I want to write the next Minecraft. But one of my favorite quotes when it comes to applications is that data matures like wine and applications mature like fish. I think if you can learn SQL as a developer, that's going to hold you in great stead for the future because it really is a powerful data access language. It really is the language that is become the de facto language even for NoSQL systems. I think the data tech is always going to change. The data technology is going to change as the hardware changes, as the scalability demands change, etc. But data access, I don't think, is going to change. SQL's been going around now for 40 plus years and seems to be getting stronger and stronger and stronger. So I really think the future as a developer, if you're coming out, no matter what field you go into, have it backed up by a good SQL language understanding, and I think you can't go wrong. As we said, it's not the strongest of the species that survives, although not the most intelligent, but the one that is most adaptive to change. So the technology will change, but the SQL access, I don't think will. So put that in your skill set, and I think you'll have a long and prosperous IT career. Thank you very much for your time. I know that was a whirlwind tour, but yeah, hopefully you enjoyed that. All the slides will be made available, obviously, to you. Plus, this will be recorded if you want to go back and watch it at a more reasonable pace. Thank you very much for being on this early morning call if you're in Europe. And if you're in the US, thank you for being on a very late evening call. But for me, it's been during business hours, so I'm absolutely thrilled. Thank you very much. And yeah, hopefully I'll see you out on Twitter or on my blog. And I'll hand back to you, Marilla.
Thank you, Connor. So recording, it's still on. I have to apologize, Connor. I forgot to start the recording on second 0. I started about a second 13. So I missed the first slide. I think the recording starts with a map where you show us where the port is. Sorry. I don't know. I can fix it, but yes, that's technology and me.
No problems at all.
Slides will be available on the EMEA site. Recording will be available there, but after the whole tour ends, we don't have time to put it there before. It was a very, very interesting history lesson, Connor. Thank you so much for it. I am sure, at least will watch it again. That's for sure. And it's something that everyone, young or not so young, it's good to watch and to learn and to find out from where we, well, the SQL from where I come, or that relational database from where I come and where we are now. I don't think we have any question. No, we don't. But if we have, you heard Connor, just find him on Twitter and ask him, and I'm sure that Connor will answer for you. Thank you all. See you in the next. See you in the next. No. Do you think analytics?
Babu,
Yes. Yes.
I can answer that for you. Do I think analytic SQLs are a good choice in relational databases? Yes, I think all of the SQL facilities available to are good in a relational database, because ideally what you're still embracing is the concept of you make an expression of what you want and the database comes up with algorithms to best do it for you. There's very few technologies other than SQL still that do that, where you don't have to worry about programmatically coming up with the best way. Because the moment you have to program it, then you have to maintain it and you have to make sure it's always going to be the best way moving forwards. One of the joys of SQL is a good database optimizer will evolve your queries over time. And yeah, don't get me wrong, no optimizer in the world is perfect, but generally they do a better job than most of our own code. That's been my experience. But thanks for the question.
Nothing else. Thank you again, Connor. Good night, California. See you on the next session. Looking forward, Connor, to see you in Bucharest.
I hope to be there soon.
We too. Have a good day, all.